Alright, in this video we're going to talk about triangle centers, which literally is the center of a triangle. And there's actually thousands of centers of triangles, but we're only going to learn 4. So let me show you what I'm talking about. If I just draw a triangle, and let's say I come from this vertex and that vertex and this vertex, where they intersect, that's a center. And it seems like there should only be, maybe one type of center, but you can actually come from the vertex and draw an altitude or a bisector or an angle bisector or a median. There's a lot of different things, different types of lines that you can draw, which then have a different name of the center. So let's just go ahead and start. The very first one that we're going to go over has to do with medians. And a median is, as shown here in this display here, it comes from the vertex and it cuts the other side in half into 2 equal parts. And as you can tell here, it's been marked. So the definition, it says a segment from a vertex to the midpoint of the opposite side. So you can immediately tell that it's a median when the other side has been marked as if it were a midpoint. Okay, before we go any further though, we need to define what concurrency is. And concurrency is when 3 or more lines, rays, or segments intersect at the same point. So this right here is a point of concurrency. So all of these triangle centers are going to be points of concurrency because they're all going to contain 3 lines that intersect, because a triangle has 3 vertexes or vertices. When 3 medians do intersect at the point of concurrency, it's called a centroid. So that's our first center, is a centroid, and that's when you draw 3 medians and they connect at one point. And you can tell that it's a median because let's just follow each line here. This vertex and then look how it cuts this one in half. And then we come from this vertex over here and it cuts this one in half. And from this one here and it cuts this one in half. So as soon as you see that they're medians, then you know that their point of intersection is called a centroid. Centroids actually have a numerical value, like we can actually solve problems based on the knowledge that it's a centroid. And what we need to know is that from the vertex to the centroid is 2/3 of the distance. And then from the centroid to the outside edge is the remaining 1/3. So if you know what one of these distances is, you can find out what the other, and in that case the whole thing. So again, this is 2/3 and then the remaining third. This is 2/3 and then the remaining third. And then 2/3 and the remaining third. The best way to solve these types of problems is to use algebra. So we have 2/3 and then 1/3. Because they are two parts out of 3 and 1 part out of 3, I think it's easier to do it algebraically as a ratio. So 2 to 1. It still becomes, it's still out of 3 parts, but if you look at it as a ratio, it helps. And I don't know if you remember from middle school, but anytime that you had to set up a ratio and solve for the total or a part of it, you could do 2x versus 1x. And that's really the easiest way to do this. So before I confuse you, let's just go ahead and look at an example. Alright, it says P is the centroid of triangle ABC, and EP, the length of EP is 8. Find the length of PC and the length of EC. So we're talking about this whole line segment right here. And they do tell us that EP is 8. The question is that the 1/3 part or the 2/3 part? And it's definitely the 1/3 part. So 1/3 of the line segment is 8. But again, I do think it's easier. They're either going to tell you the 1/3 or the 2/3 part, or they can tell you the total. In this case, they told us the 1/3 part, and they said it was 8. So we really actually have it solved already, because we can just set it up as an equation, and it says 1x equals 8. But we don't even need the 1, really. It just says x equals 8. Now that we know what x is, we can use it to solve the 2/3 part. Well, if 1x is 8, then 2 x's would be 2 8s, which would be 16, because 8 and 8 is 16 when you add them. So we know that this line segment PC is 16, so we know that. And then to find the total line segment EC, we would just take 8 plus 16, and we would get 24. So I just want to recap one more time. If they give you the 2/3 part, you're going to set up an equation, and it's going to say 2x equals some number. If they give you the 1x part, or the 1/3 part, you're just going to say 1x equals some number. If they give you the entire length, like the whole thing, then you're going to say 3x equals some number and solve that. Once you have x, then you can plug it back in and find either the 2/3 part or the 3/3 part, the whole thing. So let's do an example and just make sure that we understand. We'll just start with AY. Okay, we're supposed to find the lengths of each of these line segments. So AY is going to be this. And they gave us part of it. So we have to look at it and decide whether they gave us the 2/3 part, or the 1/3 part, or the whole thing. And looking at it, it looks like they gave us the 1/3 part. Okay, they gave us that the 1/3 of it is 6. So that's what we have right now. So this is what we're using. So 1x is 6, or in other words, x is 6. Now that we know that x is 6, we can then find out what 2/3 is, or what the whole thing is. And they ask us for the whole thing, so we're going to use the 3/3. So 3 times 6 is going to be 18, and so that would be the length of AY. AY is definitely 18. I'm going to write it down here. Once you know what x is, then you're really just plugging it in. Okay, now let's do CD. And so that's this part right here. But there's nothing in it, so we have to look a little bit further, and they tell us this part, which hopefully you can tell that that's the 1/3 part. So they gave us the 1/3 part, and they said it was 10. So in other words, x is 10. So if x is 10, then 2 10s would be 20. So the 2/3 part would be 20, and the whole length would be 30. So let's see what they ask us for. They only ask us for this part right here, which is the 2/3 part. So CD is 20. Now, BC is actually a completely different type of question. We don't need 1/3, 2/3, anything. This has to do with the fact that a centroid connects the medians. And don't forget what a median is. It comes from the vertex and it cuts this side in half. So whatever this side is, the other side is also the same. And they tell us what one of them is. So if that one's 20, so is this one 20. And if they had asked us for BY, we would be done. But they asked us for BC, which is the whole thing. So we just have to take 20 plus 20 and get 40. So BC is 40. And now we've solved for everything they've asked us for. And it's not that it's hard, but it's a lot to remember. And geometry is really bad for expecting you to remember everything you've ever learned and be able to apply it at any time. So try to always remember as much as you can, and absorb as much as you can as you learn this stuff. It doesn't seem like a lot right now, but if they give you a really big problem and there's a lot of stuff going on, you need to be able to pick it apart and look at it as individual problems. Okay, So we've gone over medians, and medians intersect at a centroid. Next, let's go over altitudes. And you probably have already known what an altitude is for years, but if you forget, it's when a shape, like any shape really, doesn't matter, but I'm just going to draw a triangle from the top, from the highest point of the shape, if you come straight down and make a 90-degree angle, that is an altitude. And the altitude can be inside of the shape, or it could be outside of the shape, or it could be on the shape itself. For example, in a right triangle, the altitude is actually part of the triangle, you know. This is the altitude of that triangle. And so is this an altitude of that triangle if you flip it over. In an obtuse triangle, the altitude is always outside. So this is the altitude. It doesn't even lay inside of the triangle. And that's fine, because altitudes can be either inside the triangle or shape, outside of the shape, or on top of the shape. And every shape, every type of shape, whether it be acute, obtuse, or right, will have a different type of altitude. So I think the best way to remember an altitude is that it's always straight up and down. It's always a vertical line, and it comes down at a 90-degree angle, so it's perpendicular. And it's never the slant height. You know, when somebody asks you to be measured, they don't expect you to lean forward or to lean backward. They expect you to stand straight up and down. So anytime that you're looking for the height of anything, which is what the altitude is, you're always going to look for a vertical, straight up and down length. And when the altitudes intersect, they create an orthocenter. That's the next center. So we've gone over medians create centroids, and altitudes create orthocenters. Every triangle has 3 altitudes, and when they intersect, it's called an orthocenter. Okay, so let's just go over the definition of an altitude. The altitude is the perpendicular segment from the vertex to the line that contains the opposite side. And I'll explain that in a minute, the line that contains the opposite side. But acute triangles, their orthocenter is always going to be inside the triangle because of the way the altitudes work in an acute triangle. But in right triangles, it's going to actually lay on the triangle itself. So if I look here, this is one altitude. Let me get a different color here. This is one of the altitudes. This is another one of the altitudes. And then the third altitude. And they actually always connect on the edge of the triangle. So this right here is where the orthocenter is on a right triangle. So they meet at different places depending on the type of shape it is. So far, right triangles the orthocenter lays on the corner of the triangle. The acute triangles lay inside, and obtuse, if you can guess, is going to lay on the outside. Because obtuse triangles, the altitudes, they're not inside. They don't actually come inside of the triangle, just like the one we just drew here. Notice that this altitude was on the outside because it was an obtuse triangle. And where they intersect is actually going to be outside, like it's going to come up here and be right about here. This will be the orthocenter of this triangle. It's not even drawn here, but that is where it's going to be. Let's recap. We have medians, and they create a centroid. We have altitudes, and they create an orthocenter. We have 2 left to go over. Alright, the next type is when you take a perpendicular bisector. So if I come and make a 90-degree angle and it bisects, then that's going to be the next type. So we're going to come over and make a 90-degree angle and we bisect. We come over, make a 90-degree angle, and we bisect. perpendicular bisectors. That's a type of lines, and where they meet, which is a bad drawing, I mean altogether, but where they meet is called a circumcenter. Oh, I can't type. Right. Okay, circumcenter. And the thing about circumcenters are that if you drew a circle on the outside edge, and this is a horrible circle, if you drew a circle on the outside edge, then each of these would be a radius of that circle. They would all be, this is equidistant from here to here, from here to here, and from here to here. So they become the radius of the outside circle. And if you draw a shape inside, like if I do a shape like this, okay, that circle is called circumscribed. And so that's another way it gets its name. I think about circumference and the fact that it creates an outside circle, and circumference is the outside of a circle, the distance around a circle. And circumcenter and circumscribed. So all of those are very similar if you can remember the perpendicular bisector part. But perpendicular bisectors, let's add it to the thing. Perpendicular, actually let's do shorthand. Perpendicular bisectors create circumcenters. So we have one type left. And the last type is when you bisect an angle. So I'm going to cut this angle in half and make those two equal. Cut this one in half, make these two equal, and then cut this one in half, oops, and make these two angles equal. And where they meet is called an end-center. And the thing about an end-center is if I draw a circle inside of the shape, which is called an inscribed circle versus a circumscribed circle, then each of these become the radius, which is pretty cool. So you have circles inside of the shape and you have circles outside of the shape, and they have different properties because they have different points of concurrency. So let's go ahead and finish this out. This is angle bisectors. And when they meet, it's called an end-center. Alright, so here's a much better drawn circumcenter. Notice that it's perpendicular bisectors because it creates 90-degree angles. And not only that, it bisects each of the sides. So these are definitely perpendicular bisectors. And when perpendicular bisectors connect, they create a circumcenter. And when that circumcenter is created, then you can use a compass and you can draw the outside circle like they did, and then each of these become a radius. So circumscribed, circumcenter, and circumference, that's what I use, and perpendicular bisector. So hopefully that helps a little bit. Okay, this is a much better drawn in-center. Notice that the circle is inside of the triangle and that each of the angles have been bisected. So, 3 and 4 are congruent, 1 and 2 are congruent, and 5 and 6 are congruent. And in addition to that, each of these is the radius of that circle. Oops, not that one, but this one. So it's kind of interesting. There's so many more different centers of triangles, but we're going to focus on these 4. Centroids are the only one of the 4 that have a mathematical property. And so a lot of the questions are going to be geared towards a centroid, just because you can use it to find values that are unknown. Okay, in your packet I put this kind of like a cheat sheet in there, and hopefully it helps. If you look at the type of triangle it'll tell you whether that center is going to be inside or outside, or all that stuff. All of the acute triangles are inside. No matter what you do with an acute triangle, your centers are going to be inside. And the right triangles, it could either be on or inside. And the obtuse triangles, it could either be inside or outside. So you get a couple different options there, and just know that they exist. If you're trying to memorize some of these, I can tell you what I remembered when I was younger. The altitudes and orthocenter. I always thought of attitude and an orthodontist, because I think when you're in middle school and you get braces, you're probably, well, maybe high school too, but you're probably at your peak when it comes to a bad attitude. And so altitude and attitude, and orthocenter and orthodontist. I always remembered that and was able to memorize that. The other three, I had different ways to memorize them, but I don't think I'm going to share them. You can probably come up with your own way. Probably what you're going to have to do in general is just be able to look at the center and say what type it is based on the lines, the intersecting lines. Like, what type of lines are they? Are they perpendicular bisectors? Are they medians? Are they angle bisectors? Or are they altitudes? And so you need to be able to look at a diagram and conclude what type of intersecting lines they are.